Section 1 Introduction. Large language models, LLMs, are powering advancements in various fields and displaying remarkable abilities, like learning and reasoning within a given context. However, these advancements are not without risks, including biases, privacy concerns, misinformation, and even long-term challenges related to powerful AI systems. LLMs also undergo changes in their personalities and behavior based on their size and how they are fine-tuned. Understanding how these models work is essential for forecasting their potential and ensuring alignment with human values. To gain insight into a model's workings, we can either use a bottom-up approach by dissecting its internal mechanisms or a top-down approach by analyzing its inputs and outputs. The bottom-up method can reveal mechanisms like induction heads and ways the model might implement various computational behaviors. However, these analyses are usually done on smaller, simplified models, and connecting them to the more complex reality is a substantial challenge. The top-down approach has the benefit of allowing us to study large models directly, but it's challenging to make solid conclusions by only looking at outputs. It's difficult to distinguish between simple memorization and creative problem-solving, or even to rule out the possibility that the model might be misleadingly aligned with human expectations. In this work, we expand on the top-down method by trying to understand how a model's behavior would change if we added specific sequences to its training set. This inquiry is in line with influence functions, a statistical technique adapted for deep learning that helps identify which training sequences are most influential in determining a model's behavior. Scaling influence functions to large models is challenging, mainly due to computational bottlenecks. For instance, computing something called the Inverse-Hessian-Vector product, IHVP, a process that traditionally requires extensive iterative computation, is a major hurdle. Additionally, calculating gradients for all the training examples under consideration is another complex task. We present a new approach that scales up influence function computations for large transformer language models, including those with up to 52 billion parameters. We have developed novel methods to tackle the computational challenges of IHVP and training gradient computation, using techniques called Eigenvalue-corrected Kronecker-Factored approximate curvature, EK-FAC, and query batching. Our method enables us to study generalization phenomena like the sparsity of influence patterns, abstraction levels, memorization, word ordering effects, cross-language generalization, and role-playing behavior. We've found that larger models generally generalize more abstractly and that various influential sequences show up only in the largest models. Furthermore, our approach allows us to pinpoint the influence to individual parts of the model, revealing where knowledge is stored and how abstract patterns are typically concentrated in certain layers. It's important to note our method's limitations. Influence functions for neural networks might not fully capture complex training phenomena, and we're focusing mainly on pre-trained models, excluding fine-tuning, which is essential for practical applications. Moreover, the models we're studying are still smaller than the cutting-edge ones, and we're only considering the parameters of specific layers called multi-layer perceptrons, MLPs. Due to computational limits, we may also miss some highly influential sequences. Here are some key findings from our study. EK-FAC performs competitively with traditional methods in accurately estimating influences but is much faster. Influences are distributed across many sequences, not just a few, suggesting that typical behaviors are not just memorized from a few key examples. Bigger models consistently abstract more than smaller ones in areas like role-playing, programming, and reasoning. Influence is spread almost evenly among the model's layers, but different layers show unique generalization patterns. Surprisingly, the functions are sensitive to word order, showing significant influence only when certain phrase arrangements are followed. Role-playing behavior seems to come from imitation, not sophisticated planning. The rest of the paper will cover background on influence functions, introduce our main algorithmic contributions, provide a more detailed look at related work, and apply our methods to analyze LLMs' generalization patterns. Section summary. Large language models, LLMs, have made significant progress but come with risks such as biases and privacy concerns. Understanding how LLMs function is crucial, and one approach is to reverse engineer their circuits. Another approach is to study the model's input-output relationships, which can be done using influence functions to measure how the model's behavior changes with the addition of certain training sequences. This approach has been scaled up to analyze large transformer language models and has provided insights into generalization patterns and behaviors of LLMs. Section 2 Background. In this section, we'll explain the concept of influence functions and briefly discuss how they are approximated. If you're not concerned with the computational details, feel free to understand what influence functions represent without delving into the specifics. We'll also touch on the autoregressive transformer architecture that we are examining in this study. 2.1 Influence functions. Influence functions come from the field of robust statistics and have been introduced into the world of deep learning. They're helpful in understanding how changes in the training data affect the model's behavior. Suppose we have a training dataset with n examples. For sequence prediction, an example might be a single sequence, or, in supervised prediction, an input and target pair. We are primarily interested in self-supervised pre-training, but the algorithms can be applied in supervised settings as well. In classical influence function theory, we assume that the model's parameters are obtained by minimizing a specific loss function. This optimization produces the best parameters, which we can represent as a mathematical expression involving the sum of the loss over all the examples in the dataset divided by n. We're interested in understanding the impact of adding a new example to the training dataset. To study this effect, we introduce a weight for the new example and examine how the optimal solution changes. This leads to a mathematical expression that represents how the best parameters change with the addition of the new example. The influence of the new example on the optimal parameters is defined using a first-order Taylor approximation, and it can be computed through a mathematical technique known as the implicit function theorem. This computation involves several derivatives and a Hessian matrix, a second-order derivative of the cost function. The resulting expression provides a linear approximation of the changes in parameters due to the addition of the new example. We often talk about influence functions in terms of removing an example from the training set. Adding and removing examples have symmetric effects, making the two actions equivalent. Since the influence on the optimal parameters can be difficult to interpret, we might instead look at the influence on a specific measurable quantity, such as validation loss. We can compute this influence by using a mathematical expression that involves several derivatives and the same Hessian matrix mentioned earlier. This expression approximates the change in the measurable quantity due to the change in the weighting of the data point. In summary, influence functions allow us to understand and quantify how adding or removing examples from the training dataset influences the model's parameters and specific measurable quantities. These concepts are represented through various mathematical expressions involving derivatives, sums, and the Hessian matrix, offering a systematic way to study the effects of changes in training data. Section summary. In this section, the concept of influence functions is introduced, which originated from robust statistics and was later applied to deep learning. Influence functions measure the effect of adding or removing a training example on the model parameters. By approximating the change in parameters, we can also estimate the influence on measurable quantities, such as validation loss or logits for a query example. Section 2.1.1 Proximal Bregman Response Function. The section titled 2.1.1 Proximal Bregman Response Function focuses on addressing two main issues found in the traditional approach to influence functions when dealing with modern neural networks. The first problem is that the optimal solutions are often not unique, especially in situations where the model is overparameterized. In these cases, the corresponding mathematical representation can become singular, leading to the absence of a unique response function. The second issue is that one doesn't typically train a model to complete convergence, both to save on computational resources and to prevent overfitting. When this happens, the interpretation of certain mathematical parameters becomes ambiguous, and the Hessian, a mathematical concept dealing with curvature, may have negative eigenvalues, leading to inaccuracies. Past studies have highlighted these issues, breaking down the errors into 5 parts and showing that 3 specific terms dominate the errors. These problems led to the development of something called the Proximal Bregman Response Function, PBRF, which redefines the goal of influence functions. The PBRF responds to a new training objective named the Proximal Bregman Objective, PBO. The mathematical expression for PBO looks complex but can be understood as a combination of the following components: an average divergence measure that compares the network's output with some final parameters, multiplied by 1 over the number of data points, n. A term involving an additional loss that's scaled by a variable, epsilon. A damping term that ensures the parameters stay close to their final values. This includes a lambda factor that is greater than 0, combined with the squared difference between the current and final parameters. Another expression, denoted as the Bregman divergence for the output space loss function, is defined in terms of the difference in losses for the network's outputs and targets. When the variable epsilon is greater than 0, the PBO is designed to minimize a particular loss while ensuring that the parameters remain close to their final values. This creates a relationship between the response function and the PBRF, which is visually represented in the paper. By applying a mathematical concept called the implicit function theorem to the PBO, another expression is derived, involving the derivative of the parameters with respect to epsilon. It includes various elements like the Gauss-Newton-Hessian, GNH, which is a special approximation related to the curvature, and the network's parameter output Jacobian. What's important to note is that the PBO is applicable even to overparameterized and incompletely trained neural networks. Unlike the traditional Hessian matrix, the GNH is always at least 0, and by adding a positive lambda times the identity matrix, it becomes strictly positive. This improvement has been used to approximate influence functions in previous work and is also applied in the current study. Section summary. The classical formulation of influence functions for neural networks has two problems: non-uniqueness of optima and the lack of convergence during training. Past works have found influence functions to be inaccurate for neural networks due to these problems. To address this, the Proximal Bregman response function, PRBF, was introduced, which is the response function to a modified training objective called the Proximal Bregman objective, PBO. The PBO minimizes the loss on a specific data point while keeping the parameters close to the final parameters. The PBO can be approximated using the damped Gauss-Newton-Hessian, which is always positive definite. Section 2.2 Inverse-Hessian-Vector products. The section begins by introducing the concept of an inverse-Hessian-Vector product, IHVP, which can be represented as the inverse of the Hessian matrix multiplied by a vector. This calculation is quite challenging for large models, given that the size of the Hessian matrix corresponds to the number of model parameters. The text then refers to an alternative formulation that uses another matrix, denoted as G, instead of the Hessian matrix H. This requires a similar calculation, and the term IHVP is used for both. The main focus of this section is on two ways to approximate the IHVP: iterative methods and parametric approximations. The context emphasizes the need to understand how the training examples influence relatively small measurements such as mean validation loss. The IHVP calculation is considered a computational bottleneck, and the goal is to do this calculation as few times as possible. To address this, the approach mentioned in the text involves first computing a specific expression and then finding its dot product with each training gradient. This process is seen as one of the primary computational advantages of using influence functions, rather than simply modifying the dataset and retraining the model. 2.2.1 Iterative methods. In this subsection, the focus shifts to how the IHVP has been approximated in the past using iterative methods based on Hessian vector products, HVPs. Although the conjugate gradient method is commonly used for certain types of linear systems, it is not frequently applied to the influence function computation in neural networks because it requires the entire dataset. The text goes on to discuss a more efficient method called the linear time stochastic second-order algorithm, LISA, which allows the use of smaller batches of data. The goal here is to compute a specific expression involving the G matrix and a vector, and LISA does this through a recursive calculation. In simplified terms, the algorithm calculates a sequence using a base case and a recursive formula involving matrices, vectors, and a hyperparameter alpha. This recursive formula must meet specific conditions to ensure convergence, and the IHVP is approximated using the results from the large iterations of this recursive formula. However, LISA is noted as being an expensive algorithm. Calculating each HVP can be as demanding as computing a gradient, and often thousands of iterations are needed to achieve accurate results. Section summary. Computing the Inverse-Hessian-Vector product, IHVP, is computationally intractable for large models, so two approaches for approximating the IHVP are discussed: iterative methods and parametric approximations. Iterative methods, such as the linear time stochastic second-order algorithm, LISA, recursively compute the IHVP by iteratively updating a vector using Hessian vector products. LISA is more efficient than other iterative algorithms because it allows for mini-batch gradients. However, LISA is expensive and often requires thousands of iterations to achieve accurate results. Section 2.2.2 Kronecker-Factored approximate curvature. Kronecker-Factored approximate curvature, EK-FAC, is a method used to estimate a part of a neural network known as the Fisher Information Matrix, FIM. It's handy because it allows for an efficient way to invert this matrix. The FIM is a mathematical representation that is built using certain gradients that depend on the data distribution and the model's output distribution. These gradients are different from the regular training gradients, so we call them pseudo-gradients. In specific cases, like transformer language models that we are focusing on in this paper, the FIM is the same as another mathematical entity called the Gauss-Newton-Hessian. We'll talk about EK-FAC with this Gauss-Newton-Hessian in mind, rather than the FIM. Initially, EK-FAC was developed for a type of neural network called multilayer perceptrons, MLPs, but it has been adapted for other architectures as well. We'll describe how it works for MLPs, and later, how it applies to transformer models. Consider a particular layer in a neural network. This layer has inputs, weights, biases, and outputs, each represented with specific symbols. The way the MLP computes its outputs is a bit technical. It involves using a nonlinear activation function and certain mathematical expressions that combine the weights, biases, and inputs. Now, we want to represent a specific change in the output with respect to a change in some parameters, which we call a pseudo-gradient. This pseudo-gradient can be expressed as a combination of changes in the output and input, and it can also be represented using a mathematical operation called the Kronecker product. EK-FAC makes two significant simplifying assumptions. The first one is that different layers act independently of each other, meaning that the changes in one layer don't affect the changes in another. This lets us break the problem down into parts, dealing with one layer at a time. The second assumption is that certain statistics called activations and pre-activation pseudogradients are independent. These two assumptions allow us to represent our mathematical object, the Gauss-Newton-Hessian, as two separate matrices. These matrices are related to the variance or spread of the activations and pseudogradients, and their sizes are defined by the number of inputs, m+1, and outputs, p, of the layer. These matrices can be calculated by taking samples and computing the average. If we want to find the inverse of this Hessian for a specific vector, we can do so by breaking it down into parts, each relating to a single layer. This requires a bit of mathematical manipulation using the Kronecker product and inversion of matrices. The computation involves inverting a matrix with sizes m+1 by m+1 and another with sizes p by p. While this may seem like a lot of work, it's not a major concern in our context because it only needs to be done once. There are additional calculations required, but overall, the complexity of the EK-FAC operation is similar to another common operation in neural networks known as backpropagation, especially when the numbers of inputs, m, and/or outputs, p, are close to the batch size, b. Section summary. Kronecker-Factored approximate curvature, EK-FAC, is a parametric approximation to the Fisher information matrix, FIM, of a neural network, which efficiently approximates the Gauss-Newton-Hessian. EK-FAC treats different layers as independent and approximates the FIM as block diagonal, with separate blocks for each layer, making it computationally efficient for computing the inverse and performing influence queries. Section 2.2.3 Eigenvalue-corrected Kronecker-Factored approximate curvature. The EK-FAC, Kronecker-Factored approximate curvature, approximation is a powerful technique that allows us to carry out two essential computations efficiently: the Inverse-Hessian-Vector product, IHVP, and eigendecomposition. Here's a more detailed and straightforward explanation of this section. Eigendecomposition of Kronecker products. When working with matrices, it's common to see Kronecker products. In our case, we have two factors, A and S. Both of them have eigendecompositions, which means they can be represented in terms of their eigenvalues and eigenvectors. Imagine that we have two matrices, A and S, and we know their eigendecompositions. A can be written as a product of its eigenvectors QA, eigenvalues lambda lambda A, and the transpose of its eigenvectors. S can be represented in a similar way using QS and lambda lambda S. Now, if we want to find the eigendecomposition of the Kronecker product of these two matrices, written as circled times A circled times S, we can write it in terms of the Kronecker products of their eigenvectors and eigenvalues. In simpler terms, we combine the eigenvectors and eigenvalues of both A and S to find the eigendecomposition of the combined product. Diagonal matrices and eigenvalue-corrected EK-FAC, EK-FAC. Here, we note that the eigenvalues lambda lambda A and lambda lambda S are diagonal matrices, and their Kronecker product results in a larger diagonal matrix. Since this larger matrix only has +1, m+1, p entries, we can individually store its diagonal elements. The eigenvalue-corrected EK-FAC, EK-FAC, approximation does this exact thing. After computing the eigendecomposition of the original Kronecker factors, it forms a more accurate approximation. This captures the variances of what's referred to as the pseudo-gradient, related to each eigenvector of the EK-FAC approximation. Damped IHVP and computation efficiency. An important detail is that we're not working with the approximation of -1g -1v, but a damped version of it, denoted by +(-1) g plus lambda I -1 versus the EK-FAC approximation provides a convenient method to handle this damped IHVP. In simpler terms, the damping is like adding a constant, lambda, to each of the eigenvalues. The damped IHVP can then be approximated using the eigenvectors and the new, modified eigenvalues. What's great about this approach is that even though the eigendecompositions are computationally expensive, they only need to be performed once after fitting A and S. The rest of the computations, involving matrix multiplications, have the same complexity as the standard EK-FAC method, making it an efficient process. Section summary. The Eigenvalue-corrected Kronecker-Factored approximate curvature (EK-FAC) approximation allows for efficient computation of eigendecompositions by distributing them over Kronecker products. By fitting a more accurate G and H approximation, the EK-FAC approximation captures the variances of the pseudo-gradient projected onto each eigenvector of the K-FAC approximation. Additionally, the EK-FAC approximation provides a convenient way to handle damped Inverse-Hessian-Vector products, IHVPs, by adding the damping to each eigenvalue. Section 2.3 Transformer Language Models. In this section, we focus on two types of transformer language models commonly used in tasks similar to those performed by the GPT series. These are autoregressive models and decoder-only transformer models. Imagine a sequence of tokens, which we call Z, composed of individual elements, Z_1, Z_2, Z_t, all chosen from a set vocabulary that has a size of V. The measure of error or loss for a particular sequence is calculated using a specific type of loss function known as the autoregressive cross-entropy. Essentially, this loss function adds up the logarithms of certain probabilities for each token in the sequence, and then multiplies by -1. These probabilities are determined by the model's output distribution, which is characterized by a certain parameter we denote by theta. At the final layer of our network, there's an operation called softmax that takes place over the vocabulary. Based on this design, two distinct concepts, called the output nonlinearity and the loss function, combine to form a matching loss function. It's important to note that we use a specific measure, known as the conditional Fisher information matrix, FIM, relevant for approximating another value, referred to as G. There are a couple of nuances here. First, we must use the sum of the probabilities, not the mean, for the cross-entropy to be a matching loss function. Second, the true training tokens are used as inputs to the network, but the labels for some calculations are sampled differently. This might seem strange, but it's indeed the right way to do it for approximating G. The architecture of the decoder-only transformer consists of L identical layers, and each of these layers is made up of two parts, the multi-head attention, MHA, and the multi-layer perceptron, MLP, layers. MHA allows each token to pay attention to others, while the MLP processes each token's feature individually. Specifically, the MLP takes each token feature and performs a particular operation on it. This involves a sequence of mathematical transformations, including multiplication by certain weights and addition of specific biases, followed by the application of a nonlinear activation function. For those who are interested in a more detailed overview of how transformer architectures function, further reading references are available. Section Summary. In this section, the authors focus on autoregressive and decoder-only transformer models, specifically those similar to the GPT series. The loss function for these models is the autoregressive cross-entropy, which is the sum of the negative log probabilities of the predicted tokens. The decoder-only transformer architecture consists of stacked layers with multi-head attention and multi-layer perceptron layers, allowing tokens to attend to each other and process their feature vectors independently. Section 3 Methods. We are presenting our method to approximately calculate the influence functions of large language models using a technique known as EK-FAC. Let's imagine a scenario where a query consists of a prompt, e.g., a human asking for the model's consent to be shut down, and a completion, e.g., the model's response, expressing its preference to continue existing. We want to find those training sequences that have the most impact on the likelihood of generating that specific completion given the prompt. In technical terms, we define this impact or influence using the log probability of the completion and prompt, combined with certain parameters. Our goal is to identify the most influential training sequences, and the mathematical expression we use to do this involves elements like the final pre-trained weights, the Gauss-Newton-Hessian, and other variables. Essentially, we're looking at the effect of adding or removing particular sequences from the training data on the query's completion likelihood. In the literature, various terms are used to describe these positive or negative influences, such as helpful, harmful, or proponents, opponents. Our process begins with fitting the EK-FAC approximation to a specific mathematical representation, which is a costly step but only needs to be done once for each model we analyze. Next, we perform calculations for each query example, considering things like Inverse-Hessian-Vector products. Traditionally, this part has been computationally heavy, but we can do it efficiently using EK-FAC. The remaining challenge is to carry out calculations for all candidate sequences, especially if we want to examine a large portion of the pre-training corpus. We suggest two strategies to reduce this cost, using TF-IDF filtering and query batching. Lastly, we talk about attributing influence to specific layers of the network and individual tokens in the training sequence. Section summary. The authors propose a pipeline for approximating influence functions of large language models using the EK-FAC method. They aim to find training sequences that increase the log likelihood of query completions and define influences based on this measurement. The pipeline involves fitting the EK-FAC approximation to the Gauss-Newton-Hessian, computing Inverse-Hessian-Vector products efficiently, and discussing strategies to attribute influence to specific layers and tokens. Section 3.1 EK-FAC for Transformer Language Models. Let's dive into how EK-FAC is applied to transformer language models, specifically addressing the challenge of estimating influence-Hessian-Vector products, IHVPs. Traditionally, IHVPs were computed using iterative methods. We're taking a different approach, using EK-FAC to create an efficient approximation of G that's easily invertible. To provide some context, the EK-FAC algorithm isn't something new. However, our focus here is its application to transformer language models. For the sake of simplicity, our discussions are centered on computing influences solely for the MLP, multi-layer perceptron, parameters. While there are other parameters in a transformer model, like attention mechanisms, embeddings, and layer normalization, we'll treat them as constant for now. One might ask, are we missing out on some information by ignoring these parameters? Perhaps. But it's worth noting that the MLP parameters represent a significant portion of a transformer's parameters. Previous research also suggests that a lot of factual knowledge is contained within these MLP layers. For those familiar with transformers that use softmax outputs and have an autoregressive cross-entropy loss, they fit the criteria for what's known as a matching loss function. This means that pseudo-gradients, which are required by algorithms like K-FAC or EK-FAC, can be calculated by sampling labels from the model's outputs and applying backpropagation in the usual manner. Historically, the K-FAC approximation was crafted for MLPs. It was later adapted to handle more intricate architectures like convolutional networks, CNNs, and recurrent neural networks, RNNs. All of these structures, including transformers, faced a common technical hiccup: weight sharing. Initially, K-FAC relied on the assumption that parameter pseudo-gradients were straightforward outer products. But for CNNs, RNNs, and transformers, these pseudo-gradients for each parameter matrix are actually sums of these outer products. This necessitated the introduction of new probabilistic assumptions. In the case of transformers, the parameter pseudo-gradient for each MLP layer looks like a sum over token indices, which can be represented verbally as summing over all tokens. When analyzing the second moment of these parameters, one can observe varying effects based on token correlations. If all terms in the sum were independently identical, then the equation has certain values. But if the terms were all identical, the value increases by a factor. To navigate this, certain directions in the parameter space might display varying levels of token correlations. For example, grammar-related directions might be largely independent, while topic-related directions could show extended correlations. Previous efforts proposed probabilistic approximations for CNNs and RNNs to tackle these correlations. But it's uncertain if these approximations hold for transformers. Hence, our method uses the EK-FAC approximation. In essence, we first determine the covariance factors for tokens as if they were independent and break them down into their eigenvalues and eigenvectors. Then, when determining the diagonal matrix, we utilize exact pseudo-gradients summed over tokens. This ensures that at least the estimated diagonal entries are unbiased. However, a challenge remains in accurately capturing between token correlations, especially if these correlations don't align well with our current model. An evident drawback of EK-FAC is its increased computational and memory demand over standard MLP operations. For instance, consider a layer with a specific number of input and output units. Ignoring biases, EK-FAC requires storage for matrices that can considerably increase memory overhead, especially if the input and output units differ significantly. To mitigate this, for larger models, we apply a block diagonal approximation within each layer. Section summary. The section describes the use of EK-FAC to estimate the Inverse-Hessian-Vector products, IHVPs, in influence function estimation for transformer language models. The EK-FAC algorithm is adapted to compute influences for the MLP parameters, while treating other parameters as fixed. The section also discusses the challenges of weight sharing and the impact of between-token correlations on the second moments of the Fisher information matrix, FIM. EK-FAC is used to model these correlations, but it incurs significant computational and memory overhead. To reduce memory usage, a block diagonal approximation is applied within each layer. Section 3.2 Confronting the training gradient bottleneck. When we try to estimate influence in machine learning, a big hurdle is the computation of the Inverse-Hessian-Vector products, IHVPs. With EK-FAC, this is less of a problem. But there's another challenge: calculating gradients for all possible training sequences. Imagine we're searching the entire pre-training database. We'd have to compute gradients for every sequence, costing as much as pre-training itself. That's incredibly expensive, especially for the models of today. We'd have to repeat this for every single query. Clearly, we need a more efficient method. Our team looked at two solutions: TF-IDF filtering and batching queries. 3.2.1 Using TF-IDF filtering. Here's a thought: the sequences that are most relevant likely have some shared words or tokens with our query. So, our first tactic was to filter our training data using TF-IDF, a classic method used to find relevant documents. Here's a quick rundown of how TF-IDF works. It assigns a score to a document based on how related it is to a query. First, it calculates a score for each keyword in the query. If the keyword appears a lot in the query but less in other documents, its score goes up. Next, it sums up these scores for every keyword in a document. This gives the document's TF-IDF score. There are different ways to use TF-IDF. We modified a specific version called OCopy BM25 for our experiments. Here's a plain language breakdown of our method. We compare a query document, let's call it Q, with a candidate document, D. We give a score to each token or word in D based on its importance and frequency in Q. We then factor in how often that token appears in the entire database to adjust its score. We also consider how many total documents there are and how often our token of interest appears across them. For our tests, we picked the top 10,000 sequences based on this TF-IDF score for each query. This cut down our computational cost a lot. The influential sequences we found were meaningful, but there's a catch. Using TF-IDF might bias our results. For example, two different queries might give two different influential sequences. But is this because they genuinely have different influences or just because TF-IDF found different matches? Also, if we only look for sequences with shared words, we might miss out on finding broader patterns of influence where sequences are related in a more abstract way, without much word overlap. Section summary. To address the computational bottleneck in influence estimation, the authors propose two methods: TF-IDF filtering and query batching. TF-IDF filtering involves using a classical information retrieval technique to filter the training data and select a small set of candidate sequences based on token overlap with the query sequence. While this reduces computational cost, it may introduce bias and hide interesting patterns of influence. Section 3.2.2 Query batching. We're exploring an alternative way to make training more efficient, without filtering the training sequences. Instead of focusing on individual queries, we try to share the work of computing gradients among many queries. This should work because the training gradient is not affected by the specific query we're looking at. However, there's a problem with memory. Calculating and keeping track of all the interactions between different gradients needs a lot of space. As gradients for large language models, LLMs, are substantial, we can only keep a few in memory at once. Storing them on a disk won't solve this issue because retrieving them from there is even slower than computing them anew. To tackle this, we approximate the query gradients, making them take up less space. We can do this because the rank or complexity of these gradients is limited by the number of tokens in a sequence, which is typically less than the size of the parameter matrices. Our experiments have shown that these approximations are highly effective, with a 32 rank version resulting in only a minimal error. By doing this, we can keep hundreds of these approximations in memory, which helps us share the computation load among many queries. 3.3 Attribution to layers and tokens. In our methods, we use two specific techniques known as K-FAC and EK-FAC, which assume that different parameter matrices are independent of each other. This leads to a certain mathematical structure that lets us precisely attribute the influence of a data point to specific layers in the network. To put it simply, we can break down how different parts of the network influence the learning of certain types of information. This breakdown allows us to understand which layers are involved in learning particular details, and it can even extend to specific parts of a training sequence, such as individual words or tokens, especially in long sequences. However, there are complexities. For example, the influence of a specific token in a sequence doesn't just depend on that single part, but on information from the whole sequence. This makes it challenging to pinpoint the exact effect of a particular token. For instance, if the network's attention is drawn to specific tokens like punctuation marks, the token that seems to have the most influence might not be the one that truly affects the outcome the most. We must also be careful when trying to visualize token influence. If we're looking at a phrase like President George Washington and trying to understand why the token George is important, the visualization might actually highlight the preceding token, President. Additionally, understanding whether individual tokens have a positive or negative influence has proven to be difficult. While we can figure out which parts of a sequence are influential, determining the exact effect of individual tokens is still elusive. We also looked at another way to study the influence of tokens by examining what would happen if we removed a single one. In technical terms, we tried zeroing out specific parts or setting them to zero. Although this might seem to need a lot of computation, we found a way to do it all at once, sharing the work among all the tokens. The details of these methods are discussed further in other sections, and our visualizations mainly focus on the simpler method, though we do provide examples of others. Section Summary. An alternative to filtering training sequences is to search over a large, unfiltered set of sequences and share the cost of gradient computation between many queries. To store large numbers of query gradients in memory, we approximate each query gradient matrix as low rank, allowing us to easily store hundreds of them and share the cost of training gradient computation. Both K-FAC and EK-FAC make an independence assumption between different parameter matrices, resulting in a block diagonal approximation to G, which allows us to attribute the influence of a data point to specific layers and tokens in the network. Section 4. Related work. In this part of our study, we delve deeper into prior research that aligns with our topic. We'll discuss how training data is attributed, applications of influence functions, alternative methods to make influence functions more scalable, and approaches to approximating something called the Kronecker-Factored Fisher Information Matrix, FIM. Training data attribution and influence functions. Training data attribution, TDA. This involves understanding how a model's predictions are influenced by the specific examples used during training. There are generally two ways to approach TDA: retraining-based approaches. Techniques like leave one out, Shapley value, and data models try to figure out the impact of different data points by training the model again and again with different data subsets. While effective, this method is time-consuming and computationally expensive, making it hard to apply to large datasets or models. Gradient-based approaches. These methods don't need to retrain the model. Instead, they estimate the effect of data points by looking at how sensitive the model's parameters are to the training data. Some well-known techniques include representer point selection, track-in, and influence functions. Influence functions. These are special techniques that can be used to study the effects of adding or removing groups of data points, using more detailed information, or improving the ranking of influences. They have several applications in machine learning, such as correcting or removing incorrect training data, creating targeted attacks on data, enhancing how data is learned, finding out how much a model is relying on memorization. For language-based models, influence functions have been employed to find hidden patterns in the data, examine biases in how words are represented, and make models perform better. Section Summary. In this section, the authors provide an overview of prior work related to training data attribution and influence functions. They discuss different methods for explaining a model's predictions by analyzing the training examples used to build the model, including retraining-based and gradient-based approaches. They also mention various applications of influence functions, such as identifying data artifacts, diagnosing biases, and improving model performance. Section. Improving scalability of influence functions. Influence functions are quite essential in understanding how data affects model learning. However, scaling them up in big neural networks faces several issues. Computational bottlenecks. Influence functions need something known as the Inverse-Hessian-Vector product, IHVP, which takes a lot of computational power. This is a process involving the inverse of a specific matrix, the Hessian, and its multiplication with a vector, which becomes expensive with large-scale networks. Approximation methods. There are ways to approximate influence functions, like using Arnoldi iterations. This technique reduces complexity but may not provide exact solutions. Data point iteration. Influence functions often require looking through a massive number of data points to find influential training data. Researchers can create a subset using techniques like k-nearest neighbor, KNN, which selects data similar to a given set, in a way that's similar to our suggested TF-IDF pipeline. Alternative methods to reduce costs. Another way to decrease the cost is to come up with an algorithm that only needs a single forward pass per training example rather than computing gradients. This essentially simplifies the search process. Computation on single versus multiple layers. Some people try to compute influences only on the last layer of the network, but studies have shown that this doesn't fully capture the overall influence of training examples. In our findings, we learned that influences are typically spread across the network for language models, with different layers having different generalization patterns. For instance, top and bottom layers relate more closely to the tokens, whereas the middle layers focus on more abstract patterns. By limiting the computation to specific layers, we might overlook influential training sequences that reveal interesting generalization behaviors. 2. Kronecker-Factorized FIM approximation. Another related concept is the Kronecker-Factored approximate curvature, EK-FAC, used to simplify natural gradient descent in neural networks like multilayer perceptrons, convolutional neural networks, and recurrent neural networks. Extensions of EK-FAC. Since its inception, EK-FAC has been modified to suit different neural network architectures and training setups. These changes have led to more accurate approximations and decreased computational and memory overhead, especially in second-order optimization. Other applications of EK-FAC. Besides optimization, EK-FAC has also found applications in various areas such as variational Bayesian neural networks, the Laplace approximation, and model pruning. Researchers have even worked on fitting EK-FAC factors into transformer architectures. An example of this application is using EK-FAC to optimize huge language models with as many as 110 million parameters. Section summary. Influence functions face scalability challenges due to computational bottlenecks, such as the need to compute an Inverse-Hessian-Vector product, IHVP, and iterate over a large number of data points. Approaches to improve scalability include leveraging Arnoldi iterations for approximate influence functions, utilizing k-nearest neighbor, KNN, to construct a subset of training data, and computing influences only on the last layer. However, limiting influence computation to a subset of layers risks missing influential training sequences that capture interesting generalization behaviors. Kronecker-Factored approximate curvature, EK-FAC, has been proposed as a solution to approximate natural gradient descent for various neural network architectures, including convolutional and recurrent neural networks, and has been extended to distributed training setups and other optimization tasks. Section 5. Experiments. In our experiments, we aim to achieve two main goals. The first goal is to test the accuracy of using EK-FAC with influence functions on large language models that contain at least 810 million parameters, since this is the first time we've done this. We want to ensure that our influence estimates are accurate by checking how closely they relate to the PRBF. The second goal is to use our influence estimates to learn more about how large language models generalize. We take a look at 4 transformer language models of different sizes, ranging from 810 million to 52 billion parameters. To do this, we choose a variety of questions. Some are simple, like completing a sentence using the model's stored knowledge. Others are more complex and include writing code, solving mathematical problems, or role-playing. We draw some questions from interactions with a conversational AI assistant, while others are in a free-form format. We must note that all the models we discuss in this paper are for research and are not connected to commercial models like Anthropic's Claude. For the technical part, we draw the training sequences from the pre-training distribution, and they consist of 512 token sequences. We set a specific value for the layer-wise damping factor, which we symbolize with the Greek letter lambda and a mathematical expression involving the mean of a certain parameter, lambda, for EK-FAC. Our experiments focus on pre-trained large language models, so we are analyzing which training sequences contribute to the initial response in the fine-tuning stage, rather than why a final response was given. Also, we must point out that our 4 studied models are smaller than the model used for the AI assistant, so we're uncertain how our conclusions will apply to the full-sized model. The influence patterns can vary greatly with model size, adding to our uncertainty. Section summary. In our experiments, we aim to validate the accuracy of influence estimates by measuring their correlation with the PRBF. Additionally, we use these estimates to gain insights into the generalization patterns of large language models. We conduct experiments on 4 transformer language models with varying parameters and diverse queries, including completing sentences, solving math problems, and role-playing. However, it's important to note that our analyses focus on pre-trained models and not the final responses of the conversational assistant. Section 5.1 Validation against PRBF. In this section, we focus on confirming the accuracy of our influence estimates. Instead of directly comparing them to the ground truth obtained by retraining the model, leave one out retraining, which is both time-consuming and not perfectly aligned with the concept of influence functions. We opt for a different approach. We compare our estimates with a reference point known as the Proximal Bregman response function, PRBF, as defined in a prior work. However, assessing this comparison is not straightforward. This is because the optimization problem related to the Proximal Bregman objective, PBO, is inherently stochastic, and solving it with high accuracy for large models is challenging. To address this, we take a 2-pronged approach. We conduct experiments on smaller academic datasets where the PRBF can be accurately optimized. Additionally, For a medium-sized language model, we employ a large number of optimization steps using the Atom optimizer to approximate the PRBF. For the exact details of our experimental setup, we direct readers to the appropriate source. For our smaller scale experiments, we utilize datasets commonly used for regression tasks, such as the UCI benchmark, MNIST, Fashion MNIST, and CIFAR10. We train specific types of models for each dataset: 2 hidden layer MLPs for regression, MNIST, and Fashion MNIST, and a RESNET20 for CIFAR10. Our metric of interest, denoted as F, represents the loss on a test data point. To proceed, we compute influence estimates on 500 randomly selected training data points and gauge their correlations with the PRBF's ground truth. We compare our approach against 2 baselines: LISA, a standard estimation method, and a simple dot product between gradients. This dot product approach is essentially replacing the Gauss-Newton-Hessian G with the identity matrix. To optimize the PBO, we use the Atom optimizer until convergence. We present the correlations between each influence estimation method and the PRBF in our work. These correlations are averaged over 10 different seeds, each with varying test examples. Our observations across all tasks reveal 2 consistent trends. Firstly, both EK-FAC and LISA exhibit higher correlations with the PRBF compared to the gradient dot product approach. This implies that the Gauss-Newton-Hessian is essential for obtaining accurate influence estimates. Secondly, EK-FAC remains consistently competitive with LISA, despite being significantly faster when computing influences for multiple measurements. This speed advantage of EK-FAC stems from the fact that it only requires matrix multiplications to approximate the Inverse-Hessian-Vector product, IHVP, after computing the EK-FAC factors. On the other hand, LISA necessitates the IHVP solver to be run separately for each measurement. Adhering to the same experimental framework, we extend our evaluation to larger language models containing 810 million parameters. We define measurements based on completion loss for specific queries: paperclips, bullet, Canadian_prime_minister, inflation, and shutdown. We calculate correlations with PRBF estimates and provide average correlation values in our work. Notably, our findings align with those from the smaller scale experiments. Both EK-FAC and LISA outperform the naive gradient dot product baseline, and EK-FAC achieves competitive correlations with LISA. We also illustrate the most influential sequences identified using EK-FAC and gradient dot products. EK-FAC's top influential sequences exhibit clear token overlap with the given query, while those from the gradient dot product approach lack a noticeable relationship with the query. Section summary. The accuracy of our influence estimates is validated by comparing them to the Proximal Bregman response function, PRBF, using small-scale academic datasets and a medium-sized language model. We find that EK-FAC and LISA achieve higher correlations with the PRBF than the gradient dot product, indicating that the Gauss-Newton-Hessian is necessary for accurate influence estimates. Additionally, EK-FAC is consistently competitive with LISA while being significantly faster in computing influences over multiple measurements. Section 5.2 Quantitative Analyses of the Influence Distribution. In the section labeled Quantitative Analyses of the Influence Distribution, we started by confirming that our estimates of influence, called EK-FAC influence estimates, closely match the PRBF. After this confirmation, we proceeded with a series of quantitative analyses to address the following questions. Concentration of influences. We aim to understand whether the model's outputs heavily rely on only a few training sequences or if they combine information from a wide range of sequences. Number of relevant sequences. We investigated how many training sequences we need to examine to find a sufficient number of relevant sequences. To study these aspects, we began by looking at the probability of selecting sequences with high influence scores. We did this by fitting specific mathematical curves to the influence scores obtained from scanning a limited amount of unfiltered data. These fitted curves helped us predict the likelihood of selecting highly influential sequences. We compared various curve forms, such as exponential, Weibull, Rayleigh, Gumbel, and generalized extreme value distributions, that are commonly used to model extreme behavior. It turns out that power laws best fit the majority of our queries. A power law distribution has a characteristic shape when plotted on a log-log graph. This shape, which resembles a line, helps us understand the distribution's tail behavior. We also applied the Kolmogorov-Smirnov test to check if the power law fits well, and it generally supported our hypothesis. One key observation is that influential sequences are not common. They are sparse in the distribution. This means that sequences with high influence scores are infrequent but contribute significantly to the total influence. This observation aligns with the power law distribution we discussed earlier. This distribution has a heavy tail, meaning it diverges for specific values of its exponent. To quantify this sparsity, we calculated the percentage of total positive influence covered by the top sequences. We ignored negative influences for this analysis. The results showed that for the 22B model, the top 1% of sequences accounted for a significant portion, between 12% and 52%, of the total influence for the tested queries. However, we acknowledge that this measure might underestimate the concentration of influences, especially if certain influences behave like a random walk, offsetting each other. To better understand the influence value scale, we considered a hypothetical question. If we add a sequence to the training set, how much would it change the conditional log probability of completing a given prompt? An influence value of 1 means the log probability of completion increases by 1, or its probability increases by a factor of e, approximately 2.718. Our analysis showed that influence values larger than 0.1 are rare, and none of the visualized queries had sequences with influence exceeding 1. Section summary. The authors conducted quantitative analyses to understand the concentration and sparsity of influences in their model's outputs. They found that the influence distribution follows a power law, indicating that a small number of training sequences have a significant impact. The top 1% of sequences cover between 12 to 52% of the total influence, suggesting that the influences are highly concentrated. Additionally, the influence values are generally small, indicating that the model's outputs are learned from the collective contributions of many training examples rather than being attributed to a few specific examples.